All right, guys. Moving on to the good stuff, the unit circle. This is probably a significant. I always say that, but man, it's a significant thing. Um, so I'm gonna walk you through what it is, what degrees are versus what radians are, why radians exist, the relevance, and why they're kind of cool. Although people give them a lot of hate, I think they're really cool to use. And then of course memorizing, haha, the unit circle. It's kind of it's not hard to memorize, but it's not easy to memorize. It's just time consuming, maybe. Um, there are some tricks that I'll try to help you out with memorizing it. Everybody has their own thing, but I'll show you a couple different things, and you can kind of be the judge of however you want to do it. So, let's get started. So, let's talk about what radians are, okay? And this is why I think they're cool. So, we've talked about degrees in the past. Now, the thing about degrees, look at that perfect circle, okay? The thing about degrees is it's sort of a man-made thing. We as people just decided one day, hey, you know what? We're gonna make a whole circle, like we're gonna call that 360 degrees, just arbitrarily. Although it's not entirely arbitrary, I believe. Here's a fun little history lesson for you. And I should Google this first, but I'm just gonna spit it out anyway. So if I'm wrong, it's fine. But I think I'm right. Back in the day, when I was growing up, in like caveman era type of times, there's these people, you've heard of the Mayans before, stuff like that. There's some people called Babylonians, I think. And again, I could be wrong here. I don't remember if it's them or not, but we're gonna assume it's Babylonians. I'm pretty sure it's them, who worked on a number system based on six, if you will, 60 maybe, 60 or six. But anyway, their number system was based on six, not 10. Like our number system is based on 10. As you know, everything kind of repeats every 10. And there's a reason they chose 6 or 60 or whatever. And that's because it was, easy. It was almost factorable to every single number. 2, 3. If you're talking about the number 60, for example, 2, 3, 5, 10. There's 15. There's a lot of numbers that will factor into 60. So when we chose degrees, we chose 360 degrees because of how broken up it could be and still be whole numbers. Like you can 360, you can break it. 30 goes into it, 60 goes into it, 90 goes into it, 2 goes into it, 3 goes into it, 15 goes into it. 20 goes into it. There's so many numbers that will factor or factors of 360 that work out really, really nicely. So you can partition it into different amounts based on if you want to partition it by 20s, 30s, 60s, 90s, 180s, 10s, etc., 6s, whatever. So it's very, very convenient to you. So that's why we picked 360 because of its convenience. But radians, long story short, radians are a natural thing that exists. It's not man-made. It's not made up. It's sort of just a relationship the circles have within themselves. So you can take any circle of any size. You can look at the one we have here. You can make a bigger circle. You can make a smaller circle. And radians will still be the same thing. So what a radian is let me use something other than red. I'm getting all geeky right now. A radian, so whatever your radius is here, right? That could be, the radius could be 1, the radius could be 2, the radius could be, 0.7, doesn't matter. The arc length, that's the exact same distance. Of course, you notice it's round because # flat earth. I'm just kidding. That was a joke. That length being the same length as the radius. So if that radius was 1, then this length here is 1, and that's a radian. If this was 2, then the length of 2 on your circle is a radian. Is 1 radian. Okay, of the same length. So the radian is it's connected to the radius. and it's the same ratio every single time. You'll always have the same amount of radians to fill a full circle, no matter what the radius is, because a circle is a circle. That proportion is not going to change. So even though radian in terms of a distance might be different, like the radian could be 1 or the radian could be 2, it's still the same ratio part of the circle. It's still basically 1/6, if so to speak, of the circle as the arc length, which is really, really neat. So it's a more natural thing. We didn't make that up because that's a property of a circle that's already existed and has always existed. So that's why I think radians are cool. Degrees are kind of man-made. We just picked a number arbitrarily, but radians always exist no matter what. So because of the natural connection they have in circles. So 360 degrees is 2 pi radians. And 180 degrees is just pi radians. So yeah, I don't really know what to say there. It's just always true. Again, no matter what your circle size is, your circumference diameter can be different lengths, but a circle is always going to be 2 pi radians around, or pi radians just half of it, 180 degrees. We're gonna look at converting radians and degrees to radians as well. So our calculator can do this, but if our calculator can, why can't we? You know what I mean? If our calculator can do it, so could us, because it's a machine, and we're not. So here we go. Degrees to radians. So we're gonna multiply by pi over 180, and if we want radians to degrees, we'll do 180 over pi. The way to not mix these up, because they basically are the same thing, is remember that whatever you're trying to go out of is what you're kind of trying to cancel out. So you see, if we start with degrees, we want to cancel out degrees. So that's why if you have, we'll see an example of this later. If I have 60 degrees and I want to convert it to radians, we're going to multiply it by pi over 180 degrees, because degrees on top and degrees on bottom, those degrees will simplify and cancel or whatever, and leave us with our radians measure. Whereas if I have a radians number, so I'll just say 2 radians or something, I'll multiply it by a degree over my radians, because my radians will cancel out and leave me with my degree value. So, because remember, this is always in the numerator over here on the left. So try not to get those mixed up. So degree, if we have negative 60 degrees, let's find out what the radians of that is. So I want to cancel out degrees, so I'm going to multiply this by pi over 180 degrees. And I know my pen's kind of glitchy there, but it's okay. So basically, this is negative 60 over positive pi over 180. And we can just reduce this. This reduces to negative 1/3, right? Pi. So there's your radians, negative 1/3 pi. Or negative pi thirds, same thing. The last one I didn't think was going to be spoiled already, but apparently it shows up anyway. So you're going from radians to degrees, so you want to cancel out radians, so you're going to multiply it by 180 degrees and then divide it by your pi radians. So you have 2 pi thirds right now. So if we just multiply this, of course the pi, the radians all cancel out. We'll have 2 times 180, which is 360 over 3, which reduces into 120. So this will be 120 degrees. So it's very simple. It's pi over 180, or it's 180 over pi, just depending upon whether you're going degrees to radians or radians to degrees. So, for if you're going to go 80 degrees to radians, then you want to cancel out degrees. So you multiply by pi and then divide by 180 degrees. So this would be 80 over 180 pi. 80 over 180 is, a number. So anyway, 4/9, 4 pi over 9, or 4/9 pi. I think you guys get the idea, generally speaking. So Moving on. Unit circles. This is where this is the stuff right here. Okay, this is the stuff. So the unit circle is based off of radius of 1. Okay. So keep that in mind. It's not just any radius. It's a radius of 1. And the values within this are super, super useful in terms of understanding a circle and its dimensions, its proportions, and whatnot. So everything you see on your screen right now is what you need to know about the unit circle. You kind of want to know, you kind of want to have that like memorized. But let me kind of show you some things that I noticed, because it's not just a bunch of randomness. There's a lot of things tied into this. Okay. So let's start with my radians here. Okay, these types of numbers. I think we already know degrees. Notice all of these are broken into 30, 45, and 60 degree spots, right? 30, 45, and 60 degrees spots. But let's talk about the radians. So this is pi over 6. Now, why is it pi over 6? Well, remember that a whole 180 degrees is pi, as you can see right here. 180 degrees is pi. We've already mentioned that, and that 360 degrees is 2 pi. Now, let's go back to the 180 degrees is pi. Notice how this right here, this 30 degrees, well, 30 degrees, 30 is 1/6 of 180, correct? Because think of this as literally a pie. You know, there are 6 slices, each of 30 degrees, that make this up, right? So this is the first out of 6, so 1 out of 6 pi, or 1/6 of pi. If that makes sense. Notice this next one is pi over 4. Well, again, that's 45 degree angles. Okay, can you go away? Thank you. All right. So the way I see it is out of pi, which remember, this half a circle is pi, right there, that slice is 1/4 of that pi, because there's 1, this would be 2, there's 3, and there's 4, right? So it's 1/4 of that pi. This one, pi thirds, a third of the pi. I don't know what to tell you, man. There you go, a third of the pi, right? So I kind of look at it like that, you know, 30 degrees, there's 6 slices. If I break this into, 30 degrees, sections, that makes 6 of them. This is 1 out of the 6. You can also think of this right here, this one here, the 2 or the pi over 3. That's 2/6, right? That's 1 slice. That's 2 slices out of the 6 that you see, which, 2 out of 6 slices is 1/3. So it's another way to see that. I hope you're seeing what I'm trying to show you. It's not the easiest thing. Of course, this is pi halves, because, you have pi right there. This is right. That's half of the pi. Again, we're not even looking at this down here. Okay, this is only broken into this hemisphere right here. So when I move over to this side, I see 2 pi thirds. And why is it 2 pi thirds? Well, because right here, right, boom, 1 pi thirds, 2 pi thirds. So that ends up being 2 out of the 3 slices of my pie. 3/4, well, again, if you broke these all into 4 sections, 1, 2, this is the third of the 4 section. 5, 6, again, if these were all broken into 6 slices, oops, wrong one there, right? 1, 2, 3, 4, 5, right here. That's the end of the 5th slice out of the 6. So if you can see that, that helps in sort of remembering parts of this unit circle. And the same goes true for the bottom. Right here, the 210 degrees, you notice how that's a 30 degree split. Well, this is your 1, 2, 3, 4, 5, 6. This is the 7 out of 6 slices. I know it doesn't make sense out of 6 slices, but pi was 1, right? So this is the 7th. Anyway, I'm getting carried away. If you broke them into 4ths, remember, boom, 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 1, 2, 3, 4, 5 fourths. If you break them into thirds, right, boom, boom. I guess there, right? 1, 2, 3, 4 thirds, right? I mean, this is how it works, dude. All right, so 3/2. I'm going to show you another way as well, if this is not making any sense. I hope you're getting it by now. As far as, so those are the radians, okay? I'll leave it at that. Those are the radians. These points are also very useful for us, and they're also, I'll explain why in a moment, but this right here is the cosine. The first one, the ones in blue are cosine, and the ones in red are sine. And I'll try my best to explain that. I really wish I had either a bigger screen or a bigger circle. I don't know. All right, but here we go. So sine of theta. So let's say, oh boy, how are we gonna do this? Okay. Let's look at this example. So I'm using this point right here, okay? Now, if this is theta down here, look at my little triangle, okay? This doesn't make any sense, but it'll work. So that's the point square root of 3 over 2 and 1/2. So I know that this length is the square root of 3 over 2, and I know this length is the 1/2. So sine of theta, remember sine, and this is 1 because remember radius is 1. Sine of theta is the opposite side over the hypotenuse. So if theta is here, we have the opposite side is 1/2 and the hypotenuse is 1. So it would be 1/2 over 1, which is just the same as 1/2, of course. So that's why it says y. Sine of theta is the y value. And you notice the y value there is 1/2. Cosine is the x value. And cosine is the x value because if you look at cosine, it's the adjacent, which is square root of 3 over 2, over hypotenuse. So you'd have the square root of 3 over 2, right, over 1, because that's the hypotenuse, which is the same thing as just the square root of 3 over 2, which is just the same thing as the x value itself. And then tangent, of course, is y over x, because you would have the opposite side, which is 1/2, over the adjacent side, which is square root of 3 over 2. Now, the reason I was a bit hesitant at the beginning of this is because my triangle is a little backwards. I probably would have been better off, making a triangle like over here or something, but it's all good. So essentially, because the hypotenuse on these triangles is 1, right, you'll have the y value over 1 for your sine. You'll have the x value over 1 for your x, but you do need to remember that tangent is y over x, which also turns out to be sine theta over cosine theta. Oof, we'll get into that in days to come. All right. Now, as far as what these points are, I guess I won't really get into too much detail, but you'll notice it's pretty much the same thing all the way around. So in terms of memorizing them, it's really easy. All the 45-degree angle ones, 45, 135, 225, and 315. They're pretty easy because they're all square root of 2 over square root of 2, or square root of 2 over 2. It's just, you got the positive because you notice this is positive and that's positive. Then you have the negative positive because, of course, this would be the negative x value and the positive y value. These would both be negative because you have the negative x value and the negative y value colliding. And then this one would be positive x value, negative y value, because positive x value, negative y value. So those are pretty easy. You just have to remember, this would be the negative, positive. This would be both negative, both positive, positive, negative. But they're all square root of 2 and 2. So those are pretty easy. These other ones, square root of 3 over 2 and 1/2, again, they're pretty much the same. But you'll notice how some of them are switched. And so here's kind of how I remember where they go if they're switched. So if I look at this point here, right, I notice that on my y-axis, boom, bada bing, that's 1/2 because it goes straight through 1/2, which is of course why the y value is 1/2. So that means this, although I can't physically see with my eye what square root of 3 over 2 is, but guess what? That must mean right here, that's got to be square root of 3 over 2, because that's obviously not 1/2. So if you're ever wondering if it's the x values square root of 3 over 2 or if the x value is 1/2, well, you can very easily figure that out by mapping it out. So if you map out, let's take this point here, right? To my x-axis, notice how we're in the negatives. I'm not even close to 1/2, so that tells me that the x value would be the negative square root of 3 over 2. And then my y value, notice it goes straight to 1/2. Again, negative 1/2, so I know the y value would be negative 1/2. So it's just a matter of you need to know it's going to be square root of 3 over 2 and 1/2. You just need to remember, of course, which one's going to be which. Square root of 3 over 2 going to be first, is 1/2 going to be first, etc. And the way you can easily figure that out is just kind of map it out. Looking at this point, if I map it out, it's going to be negative square root of 3 over 2 on the x-axis spot, and then a positive 1/2 on the y-axis spot. You, again, just need to know it's going to be square root of 3 over 2, and it's a piece of cake. So those are some tips and tricks in terms of memorizing it. Let's talk about, is this really going to go all the way through? Okay, we'll do that in class. The hand thing. Oh my gosh, dude, relax. Okay. There's a video of someone explaining this. I'll probably just link it in the description if you're curious. But basically, you take your left hand, the palm of your left hand, and the thumb and pinky finger make a 90-degree angle. So if you look at your hands, look at how your thumb and pinky finger, if you spread them all your fingers out, makes somewhat of a 90-degree angle. Now, the three fingers in the middle, your ring finger, middle finger, and index finger, are going to sort of illustrate the 30, 45, and 60 degrees that we look at in our unit circle. Now, I'm trying to remember how this goes, but I'll link the video in the description of this for someone who can explain it a little bit better than me. So let's say you put your ring finger down, right? So put your ring finger down. And what do you notice? If you count left to right, you have your thumb. I'll put it on here. I'm doing it with my hand as if you can actually see me with my hand. Your thumb, your index finger, and your middle finger, that's 3, right? So boom, square root of 3 over 2. What is it squared? I guess they're all over 2, so that's probably, easy to remember that. And then, this represents your break, and then after it, you have just 1 for the 1/2. So that can help you remember these points a little bit better as well. So if we look at, let's say, the index finger, if we put that down, then we have 1 on the left representing our 1 over 2, and then we have 3 on the right representing our square root of 3 over 2. So that's also kind of useful. And you can, of course, take your hand and use this same trick to go through all the other quadrants as well. You can do the second quadrant, the third quadrant, the fourth quadrant using the same kind of technique. But like I said, I'll put the link in the description of the video so someone else can explain it better than me. I don't use the hand trick because, I'm an old-fashioned type of person, but you're more than welcome to if it makes sense to you. All right. So come time, we are going to memorize this unit circle, and it's going to be lots of fun. Okay? Great. I already know where this. Okay. I'm going to cut the video off here, and then maybe we can do these problems in another one. But I know this video is getting kind of long already. So anyway, hopefully I did some kind of decent job explaining. Probably not, but, I did the best I could. So have a good day. I'll see you in class. Bye.